Formula for the sum of a series. To prove by induction a formula for the sum of a series, i.e. that is, a statement of the form u1 plus u2 plus ... un equals f of n, or u2 plus u3 plus ... plus un equals f of n, etc. So as in, it doesn't necessarily have to start at u1. Step 1, identify s by comparing the first and last on the left-hand side. Then prove p of s is true. Step 2, assume p of k is true, i.e. that is ... plus u3 plus ... plus uk is equal to f of k. Write down p of k plus 1, so ... plus u3 plus ... plus uk plus 1 equals f of k plus 1. Now write down the left-hand side, showing the second last term uk. So the left-hand side equals to ... plus u3 plus ... plus uk plus 1. Group the terms from the first to the second last and replace them by f of k. So the left-hand side is equal to bracket ... plus u3 plus ... plus uk bracket plus uk plus 1. So we would swap this for f of k. So it would be f of k plus uk plus 1. All that remains is to use ordinary laws of algebra to show that f of k plus uk plus 1 is equivalent to f of k plus 1. Conclusion, write down the conclusion. Prove by induction that 1 multiplied by 2 plus 2 multiplied by 3 plus ... n multiplied by n plus 1 is equal to a third n times n plus 1 times n plus 2. So what's happening here is we have a starting number 1 and we multiply it by the next number. So the next number after 1 is 2, so 1 multiplied by 2. And then we have 2, that's the next number. And the next number after 2 is 3, so 2 multiplied by 3. So then next we would have 3 multiplied by 4. And adding that to 4 multiplied by 5, and adding that to 5 multiplied by 6, and so on. So p of n is 1 multiplied by 2, plus 2 multiplied by 3, plus ... plus n times n plus 1 is equal to a third n times n plus 1 times n plus 2. So this is what we're trying to prove. So this is p of n. So step 1. The starting number s can be found by calculating the value of n, which makes the first and last terms on the left-hand side the same. In this case, though not all, the value of n is 1. Thus, s, the starting number, is 1. So if this is p of n, then this is p of 1. So 1 times 2, so that's the very first term. 1 times 2, that's term 1, is equal to a third times 1, so we're swapping that n there for 1 with brackets, multiplied by 1 plus 1, so swapping that n for 1 with brackets around it, multiplied by 1 plus 2, so we're swapping that n for 1 with brackets around it. And 1 plus 2 is 3, and 1 plus 1 is 2, and 1 is still just 1. So that's where this comes from. So then 1 multiplied by 2 is 2, and a third of 1 times 2 times 3, so this gives us 6, and a third of 6 is 2. So we get 2 equals 2, so the equation balances. Thus, p of 1 is true. Step 2. Assume p of k is true, i.e. that is, that 1 times 2 plus 2 times 3 plus ... k instead of n, k times k plus 1 instead of n plus 1 is equal to a third k instead of a third n times k plus 1 instead of n plus 1 times k plus 2 instead of n plus 2. So basically just swapped all of these n's for k's. So we assume that this is true. So now we need to prove that p of k plus 1 is true. So now we swap each of these k's for k plus 1. So we still have 1 times 2 plus 2 times 3 plus ... Then this k gets swapped for k plus 1. And this k gets swapped for k plus 1, so we have k plus 1 because we had that 1 there as well. And we have a third. Then that k gets swapped for k plus 1. Then that k gets swapped for k plus 1. But then we have this other plus 1, so we have an extra plus 1 there. And then that k gets swapped for k plus 1, and we still have the plus 2 as well. So then we simplify. So we still have 1 times 2 plus 2 times 3 plus dot 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 k plus 1. And now k plus 1 becomes k plus 2. And then we still have equals and a third and k plus 1. Then k plus 1 becomes k plus 2. And k plus 1 plus 2 becomes k plus 3. So all we did here was we simplified. So this was our assumption, and this is what we have to prove. So we came up with this in the last step on the previous slide. So now we're going to take the left-hand side, so the left-hand side, the LHS, showing the second last term, which is the last term from the assumption. So here's our assumption, and this is the last term from the assumption. So we have 1 times 2, 1 times 2, plus 2 times 3, plus 2 times 3, plus dot dot dot, k times k plus 1. So k times k plus 1. So we have basically up as far as here on the left-hand side. We're not including k plus 1 times k plus 2. We only go up as far as the second last term, which would be here, which is actually k times k plus 1. So we're grouping those together with this line. Now we do write in the last term on the left-hand side, which is k plus 1 times k plus 2, but it doesn't actually get grouped together with the yellow part. So the yellow part is up as far as the second last term. So it's up as far as here. So it goes up as far as the last term on our assumption. So we group the terms from the first to the second last, which is what we've done with this line. And in the next step, we replace by what is given in the assumption. So what we have inside this line, which is highlighted in yellow, is the exact same as what's in the assumption on the left-hand side. So if this is equal to this in the assumption, then we can substitute in place of this a third times k plus 1 times k plus 2, because that was what our assumption was equal to. But we still have our last term from the left-hand side. We still have this, k plus 1 times k plus 2, so we still write that down. So we've swapped this for this because they are equal to each other in the assumption, and then we just bring down the last term from the left-hand side. So we're going to bring down what's in blue, a third times k plus 1 times k plus 2. We're going to bring that down here. A third times k plus 1 times k plus 2. And we're also going to bring down the k plus 1 times k plus 2, but we're going to stick onto the front of it 3 over 3, so 3/3. And the reason that we're doing that is that ultimately we want to take out the highest common factor. We want to factorize both this term and this term. So by multiplying by 3 over 3, sticking on a 3 over 3, multiplying by 3 over 3 does not change its value, because that's the same thing as just multiplying by 1. So you're bringing this down here, but you're just sticking on in front of it 3 over 3, because ultimately we're going to use that to take out a highest common factor. So we have this term here, a third k times k plus 1 times k plus 2. And then we have this term here, which is 3/3 times k plus 1 times k plus 2. Now we have to look closely and see what's common to both terms. So we have a third and 3 over 3, but we're only interested in the denominator there. That's technically a third multiplied by 3. So we're going to take a third out. So we definitely have a third here. So we bring that down. And 3 over 3 is the same thing as 3 multiplied by a third. So we're really just bringing out the divide by 3 here. So we have a third as part of our highest common factor. We also have k plus 1 common to both, so we take out the k plus 1. And we also have k plus 2 common to both, so we take out the k plus 2. Now what's left in this first term? Well, all that's left there is a k, so we have a square bracket and a k, and then all that's left over here was the numerator 3, which is really 3 over 1, which is 3, so we have plus 3. So this here in pink is actually the highest common factor. So then simplifying, this just becomes a third times k plus 1 times k plus 2 times k plus 3. So we can just swap the square brackets now for normal brackets because we're multiplying. So it doesn't matter what sort of brackets we use because they're all multiplied together. And this is actually equal to the right hand side. So a third times k plus 1 times k plus 2 times k plus 3, which is the right hand side. So we were asked to prove p of k, so basically prove that this is equal to this. And we started off with the left hand side up here, and using the assumption we got down to the right hand side, which is here. So we've proven this. Thus, p of k plus 1 is true, assuming that p of k is true. So we take this for granted that this is true. So if this is true, then this is true. And our conclusion is, thus, p of n is true for all n values elements of the natural number set. Prove by induction that 1 plus 3 plus 9 plus ... plus 3 to the power of n is equal to a half times 3 to the power of n plus 1 minus 1. So p of n is 1 plus 3 plus 9 plus ... plus 3 to the power of n plus a half times 3 to the power of n plus 1 minus 1. So step 1. By comparing the first term, 1, which we can also state as being 3 to the power of 0 because anything to the power of 0 is 1, on the left hand side with the last term 3 to the power of n, so this is the last term on the left hand side, we can see that the value of n that makes these the same is n equals 0. Thus, s, the starting number, is 0 this time, it's not 1. So p of 0 is going to be 1, so the first term is 1, and that's equal to a half times 3 to the power of 0, so a half times 3 to the power of 0 plus 1 minus 1. So we're swapping that n there for 0. So this is the first term, 1. We're equaling it to the right hand side, but we're swapping that n for 0. So 3 to the power of 0 plus 1 is 3 to the power of 1. And a half times 3 to the power of 1 minus 1 is a half of 2, which is 1. So we get 1 is equal to 1, which is true. So therefore s, our starting number, is 0 this time, not 1. But it is actually usually 1. So step 2, assume p of k is true, i.e. 1 plus 3 plus 9 plus ... plus 3 to the power of k equals a half times 3 to the power of k plus 1 minus 1. So basically just swapped each of these n's for k. So this is our assumption, and we just take for granted that that is true. Now we want to prove p of k plus 1. So we basically swap each of those k's for k plus 1. So we have 1 plus 3 plus 9 plus ... plus 3 to the power of k plus 1 is equal to a half times 3 to the power of k plus 1 minus 1. And simplifying, all we have to do is simplify k plus 1, which is k plus 2. So we have 1 plus 3 plus 9 plus ... plus 3 to the power of k plus 1 equals a half times 3 to the power of k plus 2 minus 1. So this is what we want to prove, but we assume that this is true. So we're going to use this to prove this. So again, this was our assumption. We assume that this is true. And this is what we worked out in the last part of the last slide. And this is what we're going to try and prove. So again, we start off with the left-hand side. So this is the left-hand side. 1 plus 3 plus 9 plus ... plus 3 to the power of k plus 1. So if 3 to the power of k plus 1 is the last term on the left, then the second last term must be 3 to the power of k. Because if you take 1 off 3 to the power of k plus 1, you're left with 3 to the power of k. So this is the left-hand side up as far as the second last term. So it's basically up as far as here. So this is the left-hand side up as far as the second last term on the left. So we use our line here just to group those together. But we still have to bring down the last term on the left-hand side, which is 3 to the power of k plus 1. Now notice that this 1 plus 3 plus 9 plus dot 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 plus 3 to the power of k is in our assumption. 1 plus 3 plus 9 plus dot 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 plus 3 to the power of k. So we can replace this with this because these are equal to each other in our assumption. So we swap 1 plus 3 plus 9 plus dot 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 plus 3 to the power of k for a half times 3 to the power of k plus 1 minus 1. So we swap this for this. And we still have plus 3 to the power of k plus 1. But what we're going to do is stick on in front of it 2 over 2. Because similar to the previous example, we want to find a factor. We want to factorize both terms. Here's one term in blue, and here's the other term. We have two terms we want to factorize. So by multiplying the 3 to the power of k plus 1 by 2 over 2, you're not changing its value, because 2 over 2 is really 1. So you're really multiplying 3 to the power of k plus 1 by 1. So you're not changing the value of it. But in order to get a highest common factor, we need to have a half involved, because there's a half over here. Okay, so now we have our first term is a half times 3 to the power of k plus 1 minus 1. And our second term is 2 over 2 times 3 to the power of k plus 1. So now we want to factorize. So we have to have a look and see what is common to both. Well, there's a half there and 2 over 2, so we're only interested in the denominator. So 2 over 2 is the same thing as 2 multiplied by a half. So we're going to use the half part, the denominator 2. So we've got half as our highest common factor. Now I know that you might say, well, 3 to the power of k plus 1 is also common to both, but we're actually going to factorize them separately. The only factor we're going to use, the highest common factor we're going to use here is a half. So a half into a half times 3 to the power of k plus 1 minus 1 leaves us with 3 to the power of k plus 1 minus 1. So we just take what's inside the bracket and write it here. And then remember, we've already taken out the divide by 2. That's part of the half. So we're left with 2 over 1, which is 2. So it's going to be 2 multiplied by 3 to the power of k plus 1. So we have 2 times 3 to the power of k plus 1. So we have a half as our HCF multiplied by 3 to the power of k plus 1 minus 1 plus 2 multiplied by 3 to the power of k plus 1. So we have 3 to the power of k plus 1. So we have one of them there. And then we have 2 times 3 to the power of k plus 1. So we have two of them. So 1 and 2 make 3. So we end up having 3 multiplied by 3 to the power of k plus 1. So we have a single 3 to the power of k plus 1 here. So technically you could say there's 1 stuck in front, 1 multiplied by 3 to the power of k plus 1. And then we have 2 multiplied by 3 to the power of k plus 1 here. So we've 1 here, 2 here, so that makes 3 altogether. 3 to the power of k plus 1s, if that makes sense. So we have 3 of them, so it's 3 multiplied by 3 to the power of k plus 1, and then we bring over the minus. Now 3 is also 3 to the power of 1. And since we're multiplying powers by the same base, the base of 3, we add the powers. So 1 plus k plus 1 is k plus 2. So we have 3 to the power of k plus 2, and we bring down the minus 1, and we still have the half stuck on as well. So we have a half times 3 to the power of k plus 2 minus 1, which is equal to the right-hand side, which is up here. So we started with this, and we show that it is equal to this. So we have proven that this is true by assuming that this is true. Thus, p of k plus 1 is true, assuming that p of k is true. And our conclusion is, thus, p of n is true for all n values, elements of the natural number set. And this symbol here, you should recognize from sets, is a union. So also, it means and 0. So natural numbers start at 1 because they're positive whole numbers, but we have actually shown that the starting number was 0. So it's all n values, elements of the natural number set, and 0. So union 0 and 0. It's important to note that the expression 5 by 4 by 3 by 2 by 1 is written 5 factorial. So 5 with an exclamation mark, and it's called 5 factorial. And 5 factorial is equal to 120. So 5 by 4 by 3 by 2 by 1 is equal to 120. And in general, n factorial can be rewritten as n times n minus 1 times n minus 2 dot 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 times 2 times 1. And 0 factorial is defined to be equal to 1. And there is a factorial button on all modern scientific calculators. So although factorials did not come up in our examples, they do come up sometimes in actual questions. So just bear that in mind, that factorials can come up in proof by induction questions.